In class so far, we've discussed the factors or things that contribute to how fast a reaction happens, right? The kinetics of a reaction. Now I want to focus in on one of those variables, which is dealing with this idea of temperature, how it relates to the kinetic energy when something collides, and look at, well, does everything that collides with a high enough kinetic energy, will it always react? And we're going to look at that based upon what we call collision theory. Okay, so let's say we're going to go ahead and we're going to look at the reaction where we have NaCl and it's reacting with a chlorine atom here. Okay, and when that happens, we're going to see that we would get NO and Cl2. Okay, so a very basic, simple reaction that's occurring here, and we want to think for every time an NaCl molecule collides with a Cl atom, is it going to produce a reaction? Okay. Well, we're going to do this by kind of drawing this out and seeing what our molecule looks like. Okay, so we have our molecule here. We're looking at the reaction that would happen, and we notice that if we were to draw it out, we would have our molecule looking something like this. Okay, and so if we have our chlorine atom here, in order for it to make this new Cl2 molecule, it's going to have to bond to this this other Cl atom. It's not going to bond to the oxygen atom. It's not going to bond to the nitrogen atom. So that means if I have this chlorine atom and it comes and collides on the side of the molecule where there's nitrogen, well, nothing's going to happen there. Or if it comes in and it collides on the side with the oxygen, well, again, nothing's going to happen there, because it's not going to bond with that oxygen. It's not going to bond with that nitrogen. It's going to bond with that chlorine. Okay, so we see here that in order for this reaction to happen, not only is it going to have to collide with enough kinetic energy to overcome the kind of bonds here to start our bond formation with our new chlorine, but also has to collide with the correct orientation. Okay, so we'll see that we also need to have correct orientation along with the correct or enough energy that they collide with, right? Or we define that as our activation energy. So it's got to collide with enough energy to make that reaction happen. So it's got to collide here. Well, now let's go ahead and let's take it in kind of step by step as our reaction happens. Okay, we're going to go and we're going to look at kind of a reaction coordinate and energy diagram. Okay, so we're going to start here. So if we start here, we're going to have our reactants, which is, I'm going to write it like this, OnCl, and we have our chlorine atom. Okay. Well, when we have these separate from each other, they are just separate, right? So we have a certain potential energy. Well, we're going to want this reaction to happen. So we're going to say, let's say we have our chlorine atom, and now it's coming closer to this molecule. Well, when it does that, in order for this new bond to form, we're going to have to start to break this bond. Okay. Well, if we're going to have to start to break this bond, what's that going to do to our potential energy? Well, it's going to increase it, right? We pull these two atoms apart from each other, it's going to increase the potential energy there. So we're going to get an increase in energy, and we're going to end up with something that looks like this. Okay, and you notice that I've drawn in not a full bond between the nitrogen and oxygen and chlorine here, or the chlorine and chlorine here, because now what we have is we have the process where we're starting to break this bond and starting to form this bond. Right here, what we call an activated complex. Okay, so in this activated complex, we have not fully broken this bond, nor have we fully formed this new bond here. And we've had to go up and increase the energy here. Now the reason why we've had to do that is because we've started to break this bond. We've increased our energy. Now we're starting to form this bond, right? To make a reaction happen, we've got to break bonds to form these new bonds. Well, then at some point, our chlorine starts to then bond, and we're going to drop down to a new energy. Okay, and this new energy would be our nitrogen monoxide, we've now separated from that chlorine, and our Cl2. Okay. So now as our reaction's happening, we're how this collision occur, starts to break the bond, forms a new bond, and now we get to this new molecule. Well, when this happens, there's a few things that we're able to identify now from this curve. Okay, first off, we have already defined what we call our activation energy. It's got to collide with enough energy to overcome the barrier to start our bond formation. Well, we look at that here, we can call this energy hump here that we see here as our activation energy. It's the energy needed to start our reaction from happening. Okay, and then as well as we started this energy, we ended that energy. If we look at the energy differences here, well, that's going to equate to the enthalpy change for our reaction, the change in energy as we go from reactants to products. You see, we end up at a lower enthalpy. In this process, we'd see that would be an exothermic reaction. We're releasing energy. We started a high enthalpy, ended a low enthalpy. And so now we have this reaction happen here. The last thing I want to mention is that when we get to this point where we're sitting at this activated complex, okay, not every reaction has to then automatically go down to this side. What we see is that when it gets to that activated complex, it can go either way. Okay, it sits up here. It can go back down to our original reactants, which means nothing happens, and we end up with our chlorine atom and our NOCl. Or it goes down this way and we get a reaction to happen. Okay, it can do either one when it's sitting at that specific point. Okay, when we're sitting in this activated complex. Okay, and so now we see we're able to look at our activation energy. We're able to look at our reaction enthalpy change when we're able to draw this out. Okay, so now remember, in order for us even to form this activated complex, our chlorine atom has to collide with the correct location, right? If it collides here, nothing's going to happen, right? Collides here, nothing's going to happen. Collides over here, nothing's going to happen. It's got to collide with whatever it's going to start bonding with. Okay, so this gives us kind of a first step in understanding when a reaction happens, right? It's got to have enough kinetic energy to overcome this activation energy when it collides. As well, it's got to have this correct orientation.